Next session is starting in a minute. Of this day, the first speaker will be Masanori Hanada, and he will give us his new insight into large and limit as a second quantization. Floor is yours.
Okay, thank you very much. This first slide is just a copy and pasted from a conference web page. Apparently, non-commutative field theory, non-commutative geometry, matrix models are main topics in this workshop. So I think this is a perfect topic for here. So in the late 90s, Polchinski suggested that matrix model geometry is highly non-commutative, and the same holds for large and QFT, like for the n equals to 4 supermills, which is important in the context of string theory. And this is not really good news. And his claim is this is too non-commutative, and it causes a lot of headaches in the context of holography. As an example, we can consider this simple matrix model Hamiltonian. So this x hat would be n by n Hamiltonian, and this is the conjugate momentum, and we can add fermion. Or if you want the supersymmetry, then usually you don't have mass term, but the detail doesn't matter. That we have large n matrix model or QFT is the only essential part in his argument. Okay, and so let's consider this kind of matrix model. And today I almost don't mention fermion part at all. And the problem was as follows. In a normalization I have just shown, trace x squared is n squared as long as we take to first large n limit. Whether you consider excited state or ground state, it doesn't matter. The detail of the model doesn't matter. As long as the first counting holds, this holds almost by definition. Then trace of x squared would be the sum of the n eigenvalues of xi squared. So eigenvalue of xi would be n from this, trivially. The eigenvalue of x would be square root n. And maybe we have in order 1 coefficient. But this is actually too big. In the context of holography, we would want something like square root n, but we want to multiply arbitrarily small number in front of this, like 0.0001 times square root n. But we get order 1 times square root n. And furthermore, if we can also easily show that the trace of commutator squared is n to the 3, again from the first counting. Then suppose we diagonalize x1, and therefore x2, x3, and so on, we can write this in this way, very trivially, using only diagonal entries of x1, because by assumption we diagonalize x1. And this part is n. Then we have the sum of n squared terms. So each of these terms has to be order 1. That would mean when you diagonalize x1, all our matrices have large non-commutative off-diagonal entries. Trace x squared was n squared, but some contribution from off-diagonal entry is already n squared, so it's not simultaneously diagonal at all. So there is a big non-commutativity. It's a lot more than good kind of non-commutative manifold like fuzzy sphere. And his picture was like there is one highly non-commutative fuzz is sitting at the center of an eigenvalue space, and only really far away from the center, simultaneous eigenvalue can make sense. Okay, and if you want to have a good kind of fuzzy object here, then this huge non-commutativity kind of wash away good kind of non-commutativity. And it was a headache for him, and he said that there must be something wrong because it doesn't. It contradicts with the intuition from string theory. But so he knew that it's wrong, but he didn't identify exactly what was wrong. And I want to explain exactly what was wrong and how this picture changes. And in short, the answer is this. So there is no fuzz, and everywhere location can completely make sense. There is a if you take a ground state, for example, there is no commutativity at all. Okay, and I will show this why this is the actual picture. I will show, but before showing why this is correct, so let's see if this is a like a physics picture. What is good for us? And then we can use it to string theory actually. So in 1995, we then found that p plus 1 dimensional super MLs appear as a low energy effective action of D branes and open strings between them. Size of gauge matrix is a number of D brane, and the diagonal entry of matrix can be regarded as the location of D branes. So if we have a p plus 1 dimensional maximally supersymmetric MLs, we have a 9 minus p scalar field, but they describe a location, a displacement of this dp brane along this transverse direction. And off-diagonal entry describes open string excitation. So if we have a 9 minus p scalars, from one component, we can get a vector in R9 minus p, and this specifies the location of the first D brane in this space. And the two component specifies the location of the second D brane in this space, and so on. And the off-diagonal entry ij component describes open string excitation between I and j D brane. And in this picture, if we imagine like n1 D branes are sitting somewhere on top of each other, and the two of them are sitting somewhere else, and so on. And then if we add small off-diagonal excitation in each group of them, we have some block diagonal configuration, and each block would be interpreted as some band state of D brane and string with something like black hole or membrane or what to. And Banks, Fisher, Rashenka is asking, claim that this is not just an effective theory of D brane, but it can capture gravity. And also Mardasena suggested that slightly from different context, again, gauge theory can describe full theory of gravity. It's not just the effective theory. And then in this point of view, like we can embed various number of blocks, various number of objects can be encoded, one body, two body, three body. So in that sense, in large n limit, we can embed various objects in matrix, and they can interact non-trivially. So it's almost second quantization. And here I put almost because in this picture we cannot describe nothing. We have to fill matrix using some block. Okay. And then from this diagonal element called location of D brane or probe D brane point of view, then in BFSS matrix model, then we have 9 scalars, and they describe coordinate of R9. And this R9 can correspond to geometry of a black zero brane. And in the case of 4D equal to 4 superMLs, we have 6 scalars. They describe transverse R6, but this R6 is decomposed to radial direction and S5. And this radial coordinate and original 4-dimensional of 4-dimensional MLs are combined to ADS5. So by using eigenvalue of matrix, we can probe ADS5 cross S5 geometry. Actually, this kind of picture is already essentially explained in Mardasena's first paper in ADS-GFT correspondence. But if this is the case, then we cannot naively use that picture because we cannot define location of D-brane because of fuzziness of the matrix. Okay, but this is not really the case, so we can use that simple picture to see emergent geometry. But then why this picture suggested by Polchinski is wrong? The important part is that this is not just a metric, usual matrix. So X hat have Ij component. This I and j run from 1 to n. Or we can use the standard SUN generator, UN generator, and we can introduce a joint index. And each matrix entry is operator. It's not just a matrix; it's a matrix of operators. And each matrix entry satisfies canonical commutation relation. Okay, so each matrix entry has to satisfy Heisenberg uncertainty relation. Then that would mean we don't really have a uniquely defined matrix. The matrix Polchinski imagined was just matrix, usual C number matrix, but we don't have such thing. So essentially, in the past, people, including Polchinski and many people, were trying to find bug in his argument. Implicitly assumed coordinate eigenstate. By coordinate eigenstate, I mean if I act x hat, it returns some definite number. But then they encountered various pathological issues. But coordinate eigenstate is not low energy state because if we take coordinate eigenstate, then conjugate momentum is infinite. So energy of a coordinate eigenstate is infinite. So this is not low energy state. So instead, we have to use wave packet, but it's wave packet in this high dimensional space. Okay, so we can also consider superposition of the wave packet, of course. And so this phi, I just use this generic notation phi to denote wave packet, and we can use a eigenstate basis. Here I use a matrix model, but a similar argument can apply to QFT as well. Almost trivially we can from all the argument. Anyway, so we just this part is just identity. So I just acted the identity to this state, and then this is a wave function. This wave function has to be extended smoothly, not in R9, but R9n squared. In the space of matrix, it has to be spread out. So such matrix is not uniquely determined. The physically meaningful matrix obtained from a wave packet is, of course, it's a center of wave packet in this higher dimensional space. And I want to use Y to denote such matrix. Okay. And then, by definition, SUN gauge transformation moves this operator this way. So it adds this rotates this Ij. Okay, so this UN index is moved by gauge transformation, and coordinate eigenstate changes this way. So of course you can diagonalize one coordinate eigenstate if you like, but if you have a superposition of coordinate eigenstate, even if you diagonalize one specific x, others are not diagonal, and you have a non-trivial superposition again. And what happens is that if we perform gauge transformation to wave packet centered around Y, center of wave packet, location of wave packet moves, but shape doesn't change. So you cannot really take out a large matrix entry. You cannot really diagonalize this matrix. You can just diagonalize center of wave packet. And the ground state is actually corresponding to Y equals to 0. All D branes are sitting at the origin, and the non-string is excited. That's it. So there's no fuzziness. And as long as distance between center of wave packet is more larger than order 1, you can distinguish these two wave packets. So resolution is order 1, not square root n. So this is how Polchinski's puzzle is resolved. Once you know the answer, it's very straightforward. And you may think that why I'm using a state which is not gauge invariant, and you would say physical state has to be gauge invariant. And that's true, but actually we can have two equivalent ways of writing a partial function using only gauge invariant state or extended Hilbert space which contains gauge non-invariant modes. And if we use such extended Hilbert space, in which this wave packet can change under gauge transformation, we should identify these wave packets or state which connected by gauge transformation. We can do it by inserting a projection to singlet state. Okay, and they are just actually equivalent. You can show that they are equivalent. And this projection factor G hat, which is integrated out, if you rewrite it to path integral formalism, you see that this G hat is actually product of loop, and corresponding to this integration over dg corresponds to integral over gauge field A naught. Okay, so this is actually more closely related to usual path integral with gauge field. We are familiar, and I'm using this. Okay, and let's see some explicit analytic expression to understand what I said. This is almost trivial. So actually, we can use the Gaussian matrix model. Okay, Gaussian matrix model with singlet constraint. So in the past, people tried to resolve the Polchinski's argument by looking at some dynamics at strong coupling. But dynamics doesn't matter. It's just a kind of kinematical thing. And in Gaussian matrix model, Polchinski's puzzle already exists, and we can solve it in the same manner. So in this model, we have 9n squared harmonic oscillators, and the states under UN related by UN transformation are indistinguishable. Okay, this is singlet constraint. This is how operators change. Then ground state is just a Fock vacuum. So for each matrix entry, we take Fock vacuum and take a tensor product. This is ground state of this model. And then ground state wave function is just this, which is trivial gauge invariant. And it's a well localized wave packet around the origin, y equals to 0. And there is no way to diagonalize this x because this wave function cannot be changed by gauge transformation. And the same argument holds at the strong coupling. We cannot write down wave function explicitly, but we can argue that the ground state is gauge invariant in extended Hilbert space. And the generic wave packet in Gaussian matrix model is nothing but coherent state. So to get the wave packet centered around y, we can just add this kind of operator to ground state. Or more generally, if we want to introduce non-trivial momentum, we can add this to ground state. And then we can see that using that state, we can see that this wave packet actually centered around y actually moves this way. It's just a straightforward exercise. And we can easily show that the shape doesn't change, or modulo this shift corresponding to center of a wave packet. Actually, it's exactly the same shape as a ground state wave function. And if we identify center of a wave packet y with location of D brane and open string excitation, then we can have a correct symmetry enhancement pattern. For example, if we take y to be diagonal and take y D brane to be at this point in R9, then we have this expression for coherent state. And let's take n1 of y's to be the same, n2 of y's to be the same. Then from string theory point of view, we expect this enhanced symmetry, and this state actually has that enhanced symmetry. And at weak coupling, we know if D branes are separated, then open string should have a mass corresponding to the distance between D branes. But if we introduce such coupling and take this G squared to be small, then to leading order in this coupling, we can easily see that the effect. So we apply multiply this to ground state, right? And if we sandwich Hamiltonian by this, then we can just see that x hat is shifted to x hat plus p. From this, we can easily see that correct mass for open string is obtained if we have the diagonal background. So clearly, center of wave packet it should be identified with the D brane geometry, not generic pointing wave packet. Some specific pointing wave packet has to be identified with the geometry. And if we have interaction, of course, story become a bit more complicated. For example, because of the Higgs effect, we saw that off-diagonal entries have non-trivial mass. That would change the width of off-diagonal entries. And if we got a strong coupling, more non-trivial collection appear. So we have to get wave packet has to be something different, something other than simple coherent state. And I don't have a precise answer at this moment, but natural construction of at least one kind of low energy wave packet is that first give this constraint. So fix the center of wave packet and then minimize the energy. I think that this is a natural way of giving at least one sort of wave packet. And this construction gives a state, non-trivial state, which has a correct symmetry enhancement pattern and the correct Higgsing effect in recoupling limit. And in ground state, y is 0. The confined state or black hole corresponds to trace y squared is of order n squared. And the ground state is sitting at the origin. It never changes. It's just a gauge invariant. All difference are sitting at the origin. No open string is excited, so it's just a smooth geometry. And in a weak coupling limit, we could explicitly get the ground state wave function. But at strong coupling, you may ask why gauge invariant has to be ground state has to be gauge invariant. And the related question is how does a block diagonal structure naturally appear? Why such structure is dynamically or entropically favored? Or in other words, why eigenvalues tend to clamp up? That can be understood by using recently found really beautiful connection between confinement and the Bose-Einstein condensation. If we ask what is example, historically the first example of non-abelian gauge theory, many people would say it's Yamil theory. But I thought that way. But recently I realized that these gentlemen considered the historically first example of non-abelian gauge theory in the following sense. The example they considered was n indistinguishable bosons, not interacting at all, which exhibits Bose-Einstein condensation. Okay, so we want to have a partial function using a gauge invariant state, but we could also introduce a projector, and we could use an extended Hilbert space. Okay, and this expression is much more easily accessible for us. So let's use this expression. If we take a gauge group to be SUN and take a matter content to be adjoint fields, and maybe we have non-trivial spatial dimension, then it's Yang-Mills or Yang-Mills type matrix model. If we take a gauge group to be SN permutation and take fields to be fundamental field, it's a system of n indistinguishable bosons. So the example they considered is perfectly gauge theory. And if we consider n bosons in three-dimensional harmonic trap, it's almost Gaussian theory with the requirement of SN invariance. Okay, so we have this x I, and this I runs from 1 to n, corresponding to n part. And then we can easily write the Fock state, by looking at the excitation of x hat I, y hat I, z hat I, using these excitation numbers. And then we can use a permutation, sum over permutation, to have a projection to singlet sector. And then we can trivially rewrite partial function this way, which is obtained by Einstein, I think. And this part, we have inner product of n, 1 to nn, and n sigma 1 to sigma n. This sigma is Fn permutation. This part measures the amount of redundancy. If we have ground state, any permutation is the same ground state. So this sum gives n factorial. But in a generic excited state, if n1 to nn, they are all different, then only sigma equals to identity gives non-zero result here. So we get 1. And if we have n1 to nn, all different, plus many ground states here, then we get this kind of enhancement factor. And this enhancement triggers Bose-Einstein condensation, as found by Einstein in 1924. And if we have non-zero y in this block, and all this part if y is 0, we have similar symmetry enhancement. So here, such a state is invariant under SU n-m, and then volume of this is exponentially large. So that way, the confined block actually wants to curl up. And this is called by partially confined, partially deconfined state, first found by me and Jonathan Maltz, and there are many evidence that such state has to be generic. And this deconfined sector is extended bound state of strings and difference. And this is a black hole or some other object. So this way, naturally, in gauge theory, there is a natural mechanism that this block structure is preferred because of large enhancement factor analogous to Bose-Einstein condensation. And this is a generic feature of confinement, large and confined theory. So ground state of large and confined theory has to be gauge invariant similar to Bose-Einstein condensation. And this the confined sector can describe a black hole, and we can use the rest. So these differences are still peacefully sitting at the origin, but we can use these degrees of freedom to prove the geometry outside of a black hole. And we can make a small block here, and we can imagine some objects interacting with the black hole. And in large N, many blocks can be embedded, 0 block to infinite block. So in this sense, it's a second quantization. And I don't have time, so I almost skip. But I say that this projection factor is related to Poisson loop. So from the phase distribution of a Poisson loop, actually we can see how we can find the size of this deconfined block. I have to skip this part because it's a bit technical. But this is this has a counterpart in Bose-Einstein condensation. And in Bose-Einstein condensation, we can actually define Poisson loop. And the formation of BC is understood as confinement using that Poisson loop in the system of identical bosons. And this height of minimum value of eigenvalue distribution of Poisson loop. This is so-called the off-diagonal long-range order studied by Onsager and Penrose. And this is actually essentially found by Feynman in 1953. Anyways, this is a picture of a black hole formation and black hole evaporation in this picture. This is my final slide. So maybe I have to rush, I think. Yeah, so simple eigenvalue equals location picture can work. There is no problem at all. And low energy state is wave packet. This is the only important thing. Smooth bulk geometry is related to confinement, which is analogous to Bose-Einstein condensation. And the large N limit is naturally interpreted as a second condensation. I would say this is like a Banks, Fish, Rashenka, Susskind like picture working for Maldacena type duality. And to confirm the gravitational geometry explicitly, dynamical calculations are needed. And I think Monte Carlo simulation or machine learning is very promising for this. And I didn't discuss a 2B matrix model, but I think geometric interpretation in 2B matrix model may also change if we consider this kind of fuzziness. And it's fun to think if we can see partially conforming to finite and QCD. And I think there is an interesting implication to SU3 real QCD as well. And the paper is in preparation. Thank you very much.
For a beautiful talk. Can you just clarify to me how the black hole pops up? At some stage you wrote BH in there, and I was.
So here first, there are many small blocks and hovering around, and they are separated far away, and they can come close, and they form one block.
And that's a black hole.
That's a black hole. In Monte Carlo simulation, we can actually see, or simplest way to see is suppose this the confinement is taking place. Then this block is carrying almost all entropy of the system, which is entropy of black hole. This is probably the easiest way to see.
And since this is related, this is related to Bose-Einstein condensation. Have you thought of, there is a lot of analog experiments in Bose-Einstein condensation. Is there any link? Is any direction that you're taking?
But it's both Einstein condensation related to SUN gauge group, so I haven't thought about it. But maybe there is some connection.
The first historical and analogs of black holes.
Yes. So maybe there is some interesting connection, and I don't have a short answer.
Thank you.
You mentioned Feynman's paper, which is a very beautiful paper. And one of the arguments in his paper for superfluidity of helium, which I believe is the paper you referred to, was that once you take the configuration space and mod out by the symmetric group, distances cannot become very large.
Say it again.
The distances between different configurations cannot become very large, which was used by him to argue that you only excitations allowed are phonons at very low energy.
Yeah, so that's I think that's depend on the detail of the dynamics. But my fantasy is that like graviton is regarded as a phonon hovering in this BC or something. So, but I don't have a clear answer. Okay. But that's not something more than symmetry, I thought.
No, that's basically symmetry. That was the universality of the superfluidity that he argued. The roton part of the curve is not universal, but the phonon part is universal for this argument. So I was wondering if there is a similar implication for what you're doing. That would be very nice, actually.
Yes, and that's actually my collaborator Shibata suggested, and we had some discussion, but we haven't figured out the connection yet. Online.
Hello, hi, do you hear me?
Okay, hello, Silvia, can you hear us?
Okay, can I share my screen?
So our next speaker is Silvia Penati, and she will tell us something about lines and defects in ABJM theory. So the floor is yours. You have 25 minutes plus 5 for discussion.
Thank you very much. Do you see my screen?
Yes, we can.
You still see my screen?
Yes.
Okay, thank you very much. So first of all, let me thank the organizers for the kind invitation to give a talk here. I apologize because this time I cannot be there with you in Corfu, in the beautiful Corfu. Hope this will happen next year. So today I will be talking about lines and defects in ABJM theory. This is a work that I have done recently in collaboration with Luca Griguolo and Domenico Seminara and 3 PhD students, Nicola Gorini, Luigi Guerrini, and Paolo Soresina. This is basically what you can find in this paper already published, and then I will say something at the very end concerning work in progress. Okay, so let me first tell you what is the general framework I will be working in. So consider that we have a supersymmetric or a superconformal field theory whose partition function on the sphere, when you compactify on the sphere, can be exactly computed by using localization techniques. These are techniques introduced for the first time by Witten and more recently reviewed by Pestum. Let me just tell you in brief, for people who are not familiar with what it is about. So suppose you have to compute, you want to compute the partition function of your theory when the action S is invariant under some supersymmetry. Let's call it Q supercharge, which squares to 0 for simplicity. So what you can think to do is to generalize, to modify your original partition function to a z of t by adding a q exact term to your original action multiplied by a constant positive parameter t. Okay, supersymmetry implies that this quantity does not depend on t.
You're still showing us the first slide, so maybe you're using a different window, or?
Oh, whoa. No, I am. You don't see my slides going on?
We only see the first one.
Oh, sorry, I don't know what's going on. So let me do it again. Yeah, this is sharing. What about now?
Okay, now it's moving forward.
It works. Does it work? Okay,
Yes.
sorry, I was talking about this expression, sorry. So let me say again, briefly, that if you want to compute the partition function of your theory, you can modify the action of your theory by adding a Q exact term, where Q is one of the preserved supercharges of your theory, multiplied by a constant parameter T. So supersymmetry implies that this generalized partition function does not depend on T. If you just take the derivative with respect to T, you get 0 because of this constraint. Therefore, your original partition function, which is nothing but C evaluated at T equal to 0, can be equivalently computed at T equal to plus infinity, where you can apply usual semi-classical approach, and the semi-classical approximation in this exact limit becomes the exact result. Therefore, the partition function localizes at points which satisfy the equation QV equal to 0. So the loci of this exact term. Eventually, your partition function, your functional integral, therefore localizes at these configurations. Therefore, you can write for the partition function basically the integral, the sum over these null configurations times the exponential of the classical action evaluated at sigma 0 times the usual one loop determinant from quadratic fluctuations. Since we will be dealing with gauge theories, sigma 0 is typically a matrix, and therefore eventually computing the partition function in this configuration amounts to evaluate a matrix integral, which is certainly easier than a functional integral, and that's why we will talk about partition function given in terms of a matrix model. The same procedure can be applied when you want to compute correlation functions, because you can simply put some insertions inside the functional integral. The only thing you have to be sure of is that the charge Q, the localizing charge Q that you want to use to perform localization, has to be one of the supersymmetries of the insertion. So the local operators or non-local operators that you want to insert here has to be killed by the action of Q. Okay, so suppose we know how to do that, and suppose that originally the partition function, and therefore eventually the matrix model, depends on some constant parameters, which can be couplings, masses, squashing, parameters which feature Wilson loops, Wilson contours, whatever. So what we can think to do is to take derivatives of the exact matrix model respect to these parameters and then fix them at their underform or free value. What do you obtain? We obtain integrated correlators of the local operators, which actually in the original action couple to these parameters. Just to be very sketchy, suppose that in your original action, you have a master of this form for some local operator O. If you now take the n derivative of the partition function respect to M, you immediately realize that you will bring down n times the integral of O, and eventually you construct the correlation function integrated on the space-time points, okay? Therefore, if we know exactly the partition function of the theory on the sphere from matrix model, from localization, we know exact results for integrated correlators. There are many reasons why we are very interested in computing and evaluating this kind of objects. Let me just mention a few of them. If we have exact results, of course, this allows you to get information on the general structure on endpoint correlators. And in particular, if the operators and the parameters you are deriving do not renormalize, actually what you compute are correlators of protected operators, which is something quite important and interesting. In particular, if the theory you are dealing with is a superconformal field theory, because in this case, from correlators, you get informations on the superconformal field theory, because you get informations on central charges and conformal field theory data, scaling dimensions and OPE coefficients, which can be matched or can be used as an input to solve a numerical bootstrap. Certainly, computing these correlators has interesting implications for the ADS CFT correspondence, because we can, for instance, expand the result of the correlators as strong couplings, the ones that we get from the matrix model, and compare this strong coupling expansion with an holographic evaluation of the same correlators in terms of supergravity or string corrected supergravity. And the input from the matrix model can be used to determine unknown coefficients in the Witten diagram expansion that features the holographic calculation. If the operator in particular belong to a topological subsector of the theory, and with topological subsector we mean operators whose correlators do not depend on the points, on the space-time points, therefore when you talk about integrated correlators, if the correlator does not depend on the space-time configurations, the integrals become trivial. And what we get is a direct connection between correlators and derivatives of the matrix model. Finally, this is only something that I will just mention at the very end of my talk. If we take derivatives of the matrix model, which does not compute the partition function, but computes the Wilson loop, some particular kinds of Wilson loops, what we obtain are exact correlators for the one-dimensional superconformal field theory defined on the Wilson defect. Okay, with these motivations in mind, what I'm going to do in the rest of my talk is to give you direct realizations of this program, and in particular, this will concern the realization in three-dimensional Chern-Simons matter theories, and in particular, I will focus on the ABJM theory. So for this theory, I will construct the topological sector on what we call the topological line, and I will study the relationship between correlators of topological operators and derivatives of the mass deform matrix model of the ABJM theory. In the conclusions, I hope I have time to make some comments on the generalization of this program to Wilson loops, in particular supersymmetric Wilson loops, and what are the implications for the construction of the one-dimensional superconformal field theory on these dynamical defects. Okay, so let me start just to briefly review for you what is the matter content, the field content actually of the ABJM theory. I remind you that ABJM theory is an three-dimensional Chern-Simons matter theory with n equal to 6 supersymmetry. It is a gauge theory corresponding to gauge group UN cross UN. Therefore, we will have two gauge vectors, one for each gauge group, minimally coupled to a matter sector, which is built up by four complex scalars, C and C bar, and the corresponding fermions, which belong to the bifundamental representation of the gauge group. And they are also featured by non-trivial potential. Let me just remind that the gauge sector is described by a Chern-Simons action, therefore there is no dynamics in the gauge sector, whereas the matter sector has a non-trivial dynamics driven by this action, where you can recognize the minimally coupling to the gauge sector through covariant derivatives plus potentials. And we know that, well, we have two parameters in the theory. One is the gauge rank N, and one is the Chern-Simons level K. The effective coupling of the theory is N over K. And for different ranges of these parameters, this theory is dual to M theory or type 2A theory on these backgrounds. What do we know exactly about ABJM? Well, thanks to Kapustin, Willett, and Jakob, who implemented directly the localization procedure, choosing a particular supercharge, localizing supercharge that I will call QKWY. They were able to provide the exact expression of the matrix model computing the partition function of the ABJM theory on the three-dimensional sphere. This is the expression. These integrals are over two sets of Cartan eigenvalues. So these are the eigenvalues of the two Cartan subalgebras of the two gauge groups. Then we have the exponentials which come from the classical action. And this is the expression of the one loop determinant from localization. We know also some parametric deformation of this matrix model. One is the matrix model for the mass deformed ABJM, when we add a mass to the matter sector by keeping n equal to 6 supersymmetry. I will give you the exact expression for the partition function later. And one can also do some other parametric modification, for instance, computing the partition function on a squash sphere featured by a squashing parameter B. Okay, so first of all, I would like, as I said, to construct the topological subsector of the ABJM theory. We have done that by mimicking what was done by Drucker and Plewka for n equal to 4 super-Yamis in 4 dimensions, and by Dedushenko, Puf, and Jacobi for n equal to 4 theories in 3 dimensions. So what you have to do to construct the topological sector is basically choosing a particular straight line in 3 dimensions. We can choose the straight line in the third direction. Okay, we know that the line, the simple line, the trivial line, preserves half of the supersymmetries, and on the line there is a superconformal algebra realized, which is SU113 plus a residual U1 symmetry. And in particular, we are interested in the one-dimensional conformal algebra SL2 inside SU113, which is generated by P, ordinary line translations, spatial conformal transformations, and the dilatation, and the R-symmetry generators R, which are the generators of the preserved SU3 R-symmetry along the line. Then we have 12 supercharges plus superconformal charges and an extra U1. Respect to this one-dimensional algebra, all the representations are labeled by these four quantum numbers. The quantum numbers for the dilatation, the two cartons for the asymmetry, and this M eigenvalue corresponding to this U1. We can split the scalars of the theory. Remember, we have four scalars in ABJM. We can split them according to their SU3 representation. In this way, we will have a singlet Z and a triplet YA, A equal to 1, 2, and 3, and the corresponding complex and the corresponding fermions. I will be primarily focused on this part of the scalars, YA. Okay, now from the SU3 symmetry, we select another SL2 subalgebra described by these generators. And at this point, I perform the twist, which means I will consider a new twisted SL2 twisted algebra, twisted conformal algebra, generated by L plus, L minus, and L0, which are linear combinations of the original SL2 algebra plus this R-symmetry algebra. This algebra, together with the two nilpotent supercharges, which are defined this way in terms of the original supercharges, they are nilpotent and they square to 0, form a superalgebra with a central extension. What is very important, what I'm going to tell you later, is that as let's say the twisted generators, the twisted Lorentz generators, L hat, are all Q exact. So they can be written in as a Q plus or Q minus or something. Okay, once we have this subalgebra, this superalgebra, in particular with these two nilpotent supercharges, what we can do is to construct the cohomology of one of these two supercharges. You can just pick up one of them. So let me just call Q one of the two. And so this means that we look for local gauge invariant operators sitting at the origin of the line, which solve the condition to be Q closed, but not Q exact. And from the fact that both L0 and Z are Q exact, these conditions are consistent with the algebra only if the operators are required to be in the zero eigenspace of L0 and Z, which in terms of quantum numbers requires that the quantum numbers have to satisfy these two constraints. Okay, we have a simple solution, which is just take the scalars YA that I introduced before and just write down the operator trace Y1, Y bar 3, or powers of this operator. These are all and only all the operators, the local operators, gauge invariant local operators, which satisfy these conditions. So this is the cohomology of these supercharges at the origin of the line. But now using twisted translation, so translating away from the origin, the operator using the twisted translation L plus, translation operator L plus, we apply as usual this procedure, and what we end up with, starting from this operator, is a new operator at point S in terms of this biscalar of this curly Y, which are nothing but linear combinations, point-dependent linear combinations of the original scalars. Notice that here we have coefficients which depends on the point. This basically realizes the topological sector of the ABJM theory, okay? And at this point, with this kind of operators, when in the next slides you see the operator O, I always mean this operator, this bilinear operator, biscalar operator. These are very important because at this point, I want to compute correlation functions for these topological operators defined in the usual way. And one can immediately realize that These correlation functions are in ABJM, in general non-vanishing, and they can acquire finite quantum corrections. Why finite? Because these operators are still protected by a fraction of supersymmetries. In fact, they preserve 1/6 of the original ABJM supersymmetry charges. Okay.
5 more minutes.
Okay, thank you very much. So at this point, we can immediately see that because L plus is a Q of something, is Q exact, any correlator made up by these operators is point independent. If you act with the derivative with respect to any point, you get 0. Okay, now, as I said, I want to compute these operators, this correlator using the matrix model. How can I do it? As I said, if I want to compute this correlation function using localization, I have to use a localizing supercharge, which kills these operators, according to which, these operators are still invariant, okay? And this is not, unfortunately or fortunately, this is not the KWY supercharge originally used by these people. We have to use, in fact, the cohomological charges Q plus and Q minus. Okay, if we do that, what has been proved and shown in this paper by the Dushenko, Poisson, and Jacobi is that using this different supercharge, we end up with a different expression for different, but of course equivalent expression for the partition function of the IBJM theory, which now is given by the product of a gauge sector, which is still a matrix model for the gauge sector, times a one-dimensional Gaussian model localized on the gray circle on S3, which is nothing but our topological sector. To make the long story short, if we now also deform the partition function, adding some mass term for the scalars of the theory, what we get is that the original KWY partition function, or the original matrix model, is equivalent to this other gauge matrix model times this one-dimensional quantum mechanics. Okay. Now, it's an easy game to see that if this is true, if you take on the right-hand side the derivatives with respect to m, you will bring down many times the integral of this object, which is nothing but our topological operator. Therefore, the integral of correlation functions of our topological operators should be equal to the n derivative with respect to m of the original mass deform matrix model of the ABJM theory. Okay, this is just a conjecture because there is no direct proof in particular for ABJM. So what we did was to prove, or at least provide evidence of this conjecture, focusing on the two-point function. Okay, so this is what one should prove, having in hands the exact expression for the mass deform partition function for the ABJM theory, which is this one. This is nothing but what I already showed you, including the mass deformation. Okay, now what we can do is on the right-hand side, just take the second derivative of this expression and expand it for lambda, the coupling constant small. Sorry. Okay, so you are perturbative at this point, and you will get this expression up to 2 loops. On the left-hand side, what you can do is just to compute. I don't know why it doesn't work. Okay, it's just to compute, you can just compute the correlation function using an ordinary perturbative approach, which means 2 loops computing this kind of diagrams. The calculation is quite involved. Of course, I don't give you any details. Let me just tell you that from this calculation, we got exactly the same expression. So there is perfect matching, and therefore this is this is one non-trivial proof that this identity indeed holds. Okay. Now, what we could do next, this are just my conclusions. Still in the kinematical case, we should, of course, assume at this point that the identity holds in general, and we could go further and compute 4 or higher point topological correlators taking higher order derivatives of the matrix model and extract information on the superconformal field theory data in ABJM. But as I said, if I have just one minute left, the most interesting thing that we have been doing these days is try to generalize this construction to dynamical defects, which means replace the line, the trivial line that I was considering, with a BPS Wilson line, which is the ordinary expression for Wilson lines, where here the ordinary connection is generalized to something which includes also couplings to matter, to the matter sector, tuned in such a way that this operator preserves a given amount of supersymmetry. Okay, for this kind of Wilson loops, we know a matrix model computing the expectation value. So we expect that if we now take the derivative with respect to some parameters of this other matrix model, what we will end up with is a correlator of operators on the Wilson line, which means where the vacuum, the trivial vacuum, is now dressed by the Wilson line. Okay. The questions, the open questions we should answer are these operators still topological? Probably not. So what is, do we have a way to construct topological operators on the Wilson line by applying twisting, as we did for the trivial line? I can only tell you that there is no straightforward generalization of what we did for the line to the Wilson line, because in this case, in the presence of Wilson line, all the superconformal algebra on the line has to be covariantized, because the Wilson line is invariant under covariant supercharges. And therefore, what we are experiencing in this day is that the elementary operators that were protected operators giving rise to topological sector on the line are no longer protected on the Wilson line. Therefore, there is no trivial way to define a topological sector in the presence of a Wilson line. And in particular, there are recombination effects where short multiplets combine to give rise to long multiplets, non-protected long multiplets, and this is something which has to be better understood. But as I said, this is just work in progress. Okay, so we stop here. I thank you for your attention.
So maybe one quick question or comment, either from the auditory or. Yeah.
So thank you, Silvia, for the beautiful talk. This is Rita.
Oh, hi, Rita. Hi.
Hi. So I'm sorry for the trivial question, but you mentioned the superconformal algebra, right?
Yes.
And I was here on a line, but I really don't understand this SU113. Why the 3? You know, I'm used to the SU2,2,1, which is the twister, the super twisters. Now I don't understand the 3, you see?
3, well, 3 is coming basically because you have basically SU3. I mean, the number of supersymmetries that you preserve with the line provides you, I mean, the supercharges are in SU3 representation. Okay, so sorry, maybe I should go back to.
Yeah, so this is you superimpose that it is 3.
You know, the number of
the
number of supercharges that are preserved on the line are Q1, Q2, Q3, which are basically linear combinations of the original ABJM supercharges. So originally you have 24 supercharges, 12 plus 12, and they realized this OSP6 4.
So into an OSP, okay.
And but then you know, yeah, it breaks down to.
Okay, thank you.
Okay.
Okay, so let us thank the speaker again to keep on track.
Thank you. Thank you very much.
And our next speaker is Vladislav Kupriyanov with his talk about Poisson gauge theory. Vladislav, can you hear us?
Yeah, I'm here. Can you see my screen?
Yes, we can see it now. So we have 25 minutes plus 5 for discussion.
Okay, thank you. First of all, I would like to thank the organizers for the invitation to speak here. It is always a pleasure to be there in Corfu, unfortunately this year in the remote way. So I will speak about the Poisson gauge theory. Mainly this talk is based on these two recent papers, one of them, the first one in collaboration with Richard Szabo. So here is the outline of my talk. I will start with the motivation and the formulation of the problem, that is the formulation of the non-commutative gauge theories with non-constant non-commutativity parameter in the semi-classical limit. I will discuss the mathematical tools, how to construct such a theories, and then I will proceed with the construction, that is the gauge covariant derivative, the field strength, the Yankee identity, action principle, etc. I will also discuss the precise examples like the SU2-like linear Poisson structure and Kappa-Minkowski structure. Then I will show the Maxwell-Poisson equations, and we'll end up with a brief discussion of all this. So previously this week, yet during the Humboldt Collect, Richard Szabo gave a nice talk on braided non-commutative gauge theories, and he explained how non-commutative gauge theories appears in the context of string theory, that is as a low energy limits of some string theoretical models. But actually, yet quite before the string theory, yet in the early days of quantum mechanics, it was known that space-time, classical space-time, cannot be measured with an absolute precision, because the arguments from the quantum mechanics in combination with the arguments from general relativity indicates that space-time should be non-local on the very short distances. And the way how we can introduce this feature into our theory in the consideration is to suppose that the operators which represent the coordinates of space-time are non-local, are non-commutative. That is why they cannot be measured simultaneously, and we end up with the non-commutativity. And in general case, if we suppose that non-commutativity can be a kind of effective way how to take into account the effects of quantum gravity, the non-commutativity parameter should be non-constant if we are talking about gravity. So in order to take this into account in the field theory, a kind of standard way of doing is the following. Instead of working with non-commutative operators, we may work with commutative functions, on some well-defined commutative manifold. However, we should substitute the pointwise product of functions with the star product, this one here, which is non-commutative. However, when we talk about gauge theory, the situation is becoming much more complicated, since the gauge theory normally is based on the notion of a covariant derivative. This object here, with the main property is that it should transform covariantly under the gauge transformation, that is in the absolutely the same way like the matter field. And now, if we just take and substitute all pointwise products with the star product, we have a problem with the violation of the Leibniz rule for the star product because of this term here, which also depends on coordinates. So when we take a partial derivative of a star product, partial derivative also will act on the non-commutativity parameter, and that is why the Leibniz rule will be violated. And because of the violation of the Leibniz rule, this nice property of a covariant derivative also will be violated. And that is why actually, if we just take and substitute all pointwise products with the star products in our gauge theory, we will lose gauge invariance. And thus we go to the statement of our problem. So we are looking for the non-commutative theory satisfying the following two properties. We need gauge invariance of this theory because it is a fundamental property of our universe. And also, we would like to have a correct commutative limit. In this talk, I will discuss the U1 gauge theory, that is Maxwell theory. So essentially, we would like to understand how the fundamental interactions, like the electrodynamics, will be affected by the presence of quantum gravity, if we suppose that the non-commutativity is an effective way to describe the quantum gravity. And in this talk again, I will simplify a little bit. So we will discuss the semi-classical limit. The semi-classical limit is defined like this. So instead of working with the star commutator, we will work with the Poisson bracket. And the semi-classical limit of the full non-commutative gauge theory will define, as I will explain a bit later, the Poisson or almost Poisson gauge theory for non-associative gauge theories. Again, earlier this week, Richard has already discussed the previous approaches existed to the solution of this problem, to the construction of a consistent non-commutative gauge theory. I will not spend my time here repeating all that. I will just mention our previous approach, which we proposed in collaboration with Munich string theory group about 3 years ago, and I reported about this approach in 2019 in Corfu. And this approach is based on L-infinity algebras. We called it L-infinity bootstrap. Actually, this approach is a really powerful tool for the construction of order-by-order deformation of gauge theory. But when we need to obtain some explicit all orders results, normally we need to use some additional consideration. So in this talk today, I will discuss these additional considerations, which we call symplectic embedding, right? And also this approach of the L-infinity algebra is a bit complicated, and while the approach I will discuss today is much simpler. So let me be more precise and formulate the problem. If we start with just talking about the non-commutative gauge algebra, it is determined like this here, the commutator of two non-commutative gauge transformations acting on a gauge field is again a gauge transformation, however, corresponding to the star commutator of two gauge parameters. And since we are working with the semi-classical limit, so semi-classical limit of the full non-commutative gauge algebra defines the Poisson gauge algebra, which is written here in red, right? The commutator of two gauge transformations is again a gauge transformation, however, with the Poisson bracket of two gauge parameters. So the gauge transformations which close this algebra and have the standard U1 gauge transformation in the commutative limit are called Poisson gauge transformations. Now let us discuss how to construct the representation of this algebra. If theta is constant, then one may easily check that this kind of standard form for the gauge transformation, that is just a derivative acting on gauge parameter f plus a Poisson bracket, which stands here instead of a star commutator, right? So this expression will close this algebra. However, if theta is non-constant, and in this case we will have the violation of the Leibniz rule, then the same expression will not close this algebra anymore. And to solve this problem, we will have to introduce some corrections with derivatives of gauge parameters here in order to compensate the violation of the Leibniz rule. And actually, the way that we found how to solve this problem is to work in the extended space, which is called symplectic embedding. So first, I will discuss very briefly, I will say very briefly some words about symplectic embeddings of the Poisson manifold. And then I will already say how, using the symplectic embeddings, we construct the Poisson gauge transformations. Okay, let us start with a given Poisson structure here. And for given Poisson structure, we may construct a bigger symplectic structure or symplectic algebra. That is, to each coordinate x, we introduce an additional momenta or additional coordinate p. And we need to construct the set of symplectic brackets. Symplectic in the sense that the Poisson bracket should be non-degenerate. And they also should satisfy the Jacobi identity. Okay, the Jacobi identity for this set of brackets implies this partial differential equation on the matrix gamma, which determines the symplectic embedding. So theta is given, and I need to find the gamma in order to have the algebra of Poisson brackets here. And actually, talking about this equation, we know how to solve it. Here are the first orders of the perturbative expansion. The recursive formula can be found in my paper 2 years ago. But moreover, for some specific choices of the Poisson structure, we have some explicit, absolutely explicit constructions. For example, for linear Poisson structures given here, where f here are structure constants of Lie algebra. So the symplectic embedding is given by this formula here through the matrix valued function here, which is given here. Moreover, for some more particular choices of the structure constant here, we can diagonalize this matrix M here and obtain even more, let's say, workable expressions, like here, for example, for the SU2 structure, which is defined by this Poisson structure. The expression for the symplectic embedding has this form here. And for Kappa-Minkowski space corresponding to this Poisson structure, the symplectic embedding can be found, for example, in this paper and is given by this expression here. But actually, we can construct in this way not only the symplectic embeddings of linear Poisson structures, we can also work with non-linear structures. So like this one here. Actually, this Poisson structure here is obtained from this one by rescaling of the coordinate, by the coordinate change. The difference is that this one is linear, so in principle, the non-commutativity is growing on the infinity, while here we have this Gaussian exponential, and on the infinity it goes to zero, so a kind of local non-commutativity. But since they are related by the coordinate transformation, so using the symplectic embedding of this SU2 structure, we can also construct the symplectic embedding of this non-linear structure. Right, so these were a few words about the symplectic embeddings. Now, using the symplectic embeddings, we can construct this Poisson gauge transformation. To overcome the problem with the violation of the Leibniz rule, instead of working with standard partial derivative, we can introduce this object that we call twisted partial derivative. It is defined as a Poisson bracket of a gauge parameter with the p variable given here. And this twisted partial derivatives, they behave in a kind of similar way as a standard partial derivative. They commute, and actually they do satisfy the Leibniz rule here. It just follows from the Jacobi identity for the Poisson brackets in the extended space. Right, so substituting just partial derivative with a twisted derivative, we can rid of the problem of a violation of the Leibniz rule. However, there is a price to pay, because now this twisted partial derivative depends explicitly on these auxiliary non-physical p variables. And actually, we found the way also how to rid of these non-physical variables. It is formulated here in this theorem. This expression here, which is obtained from the larger space by imposing this constraint, actually closes the Poisson gauge algebra and reproduces in the commutative limit the standard U1 gauge transformation. So actually this theorem provides us with a solution of a problem of a violation of the Leibniz rule and gives us the expression for the Poisson gauge transformation, right? So now we have the Poisson gauge algebra and its representation. That is, we have the kinematical part of a gauge theory, and now we may proceed to the dynamics. We may now ask how to construct the covariant object, that is the gauge covariant derivative, the field strength, etc., equations of motion. So we introduce here the matter field psi, and we define the gauge transformation of a matter field in this way to be consistent with the semi-classical limit. So such a determined gauge transformations also close this Poisson gauge algebra, but now on matter field. And now we may ask how to construct the gauge covariant derivative, that is object that should transform covariantly under the gauge transformations, and also the object which should reproduce the standard derivative in the commutative limit. And again, we may formulate the following theorem, that this object determined here in red satisfies these two properties if the matrix rho here satisfies this equation here. Again, it is a partial differential equation, but again, we know how to solve it. Here is the perturbative solution up to the second order in theta, and a bit later I will give some explicit examples in all orders in theta. But before that, let me just say that now, having in hand the covariant derivative, we may proceed to the construction of the field strength, etc., etc. So the commutator relation for the covariant derivative determines the field strength. This object here, which, as we can prove, as was proven here in my recent paper, it transforms covariantly under the Poisson gauge transformations, and it reproduces the standard Abelian field strength in the commutative limit. So it is the Poisson field strength. In addition, we have here the expression for the deformed Bianchi identity. It is written here also in red. So now let me show some explicit examples of the Poisson gauge transformations and Poisson field strength. Again, for the SU2-like Poisson structure, which corresponds to the rotational invariant non-commutative space, we have this expression for the Poisson gauge transformation. Again, it was constructed from the symplectic embedding, and the explicit expression is 1. And for the matrix rho, which enters the definition of the Poisson field strength and the covariant derivative, we have this explicit expression here. It is explicit all orders in theta, right? Another example is Kappa-Minkowski space, which we discussed the last year with Max Kurkov and Patrizia Vitali. So the Poisson structure is this one. And for this Poisson structure, we find this Poisson gauge transformation. And for the matrix rho, which enters the definition of the field strength and the gauge covariant derivative, we have this expression here. I'm not giving here the explicit form of field strength because it is kind of very big. But so having this rho, you just substitute here and you have this expression, right? Now, once we have these covariant objects, the covariant derivative and the Poisson field strength, we may proceed to the construction of the Lagrangian, which is also covariant. It transforms covariantly under the Poisson gauge transformation. And using this Lagrangian, we may using the gauge covariant Lagrangian, we may construct the gauge invariant action with an appropriate integration measure. Already from the gauge invariant action, we may just obtain the Euler-Lagrange equations, which in the case of SU2-like structure have this form here. For Kappa-Minkowski, we will have some additional terms because of the non-trivial integration measure here in the action. But for SU2-like structure, just this form of Euler-Lagrange equation. So these equations are in fact the deformation, the consistent deformation of the first pair of Maxwell equation. And Bianchi identity provides us with the second pair of Maxwell equations. So actually the problem that I formulated from the very beginning, how to construct the consistent deformation, the consistent gauge invariant deformation of Maxwell theory is given here. Here we have the deformation, gauge invariant deformation of two pairs of Maxwell equations, right? And in the commutative limit, we have the standard Maxwell equations. Finally, let me just note about the arbitrariness. Since the symplectic embedding is not unique, actually, if we have one symplectic embedding, we can make a change of coordinates in this auxiliary and this extended space, which does not change the Poisson bracket between X, and we will get another symplectic embedding of the same Poisson structure. Since our construction relies on the symplectic embedding, for this new symplectic embedding, we will get some kind of new gauge theory. However, it is shown in my paper, in my recent paper, that different theories which correspond to different symplectic embeddings of the same Poisson structure are related by the invertible field redefinition defined here. And that is why actually physically they are the same. The gauge orbits are mapped onto the gauge orbits. And now let me go to the discussion. Actually, Poisson gauge theory is a self-consistent approximation of the full non-commutative gauge theory. It is first order in the Planck constant h bar, but all orders in the non-commutativity parameter. All formulas here are exact, they are not approximated, right? To construct the Poisson gauge theory, we use a very well understood mathematical tool in symplectic geometry, which is called symplectic embedding. It is really very well understood. And the symplectic embedding defines the Poisson gauge transformation, which close this Poisson gauge algebra. To define the dynamics, we need to solve an additional equation which determines this matrix rho, which in turn defines the field strength, Poisson field strength, and the gauge covariant derivative. However, we know how to solve this equation. We have some explicit examples of the solution of this equation. And quite recently, in collaboration with Max Kurkov from Naples, we found the solution of this equation for any linear Poisson structure and Poisson structures which can be obtained from linear Poisson structure by the invertible coordinate deformations. The symplectic embeddings are not unique. However, the Poisson gauge theories, which correspond to different symplectic embeddings of the same Poisson structures, are related by the invertible field redefinitions that is correspond to the same physics. And there are some open questions. This model of a Poisson gauge theory is quite new, so it is interesting to understand if there is some reasonable physics behind this. So we need to study the classical solutions of these equations of motion and see what kind of physics may stay behind. It is interesting also to discuss the almost Poisson gauge theory, which correspond to the non-associative deformations which come from string theory. So with Richard Zaba, we constructed almost Poisson gauge algebra, but we don't have yet the dynamics on this gauge algebra. And we may proceed to the full non-commutative gauge theory, that is, go from the Poisson bracket to the full star commutator. So this is a kind of open questions for the future, and I'm finishing here. Thank you for the attention.
Thank you for the interesting and perfectly timed talk. Are there any questions in the audience? Maybe switch them.
Yes, hi. I have a question. Could you please go back to the page where you introduced these symplectic embeddings in the beginning?
Here.
Yeah, exactly. Can you explain again, first of all, so you have, I mean, if you're given a Poisson structure, let's say in 4 dimensions, how can you always, I'm a bit confused. So do you change the dimension of the symplectic space, or how can you introduce a number of commuting p's? That's the first question.
Well, actually, this I can do in any number of dimensions. So this is given, the dimension of X space is given, and I don't do anything with it. So it is given the Poisson manifold, suppose with dimension D. And I introduce another D variable, so I'm constructing the 2D symplectic manifold. And in this symplectic manifold, I require that the Poisson bracket between the auxiliary variables should be 0. This I need because of my theorem, how to construct the Poisson gauge transformations. And only I end up with this matrix, gamma matrix, which determines the Poisson bracket between old coordinates and the new ones. And I know how to construct it, just perturbatively.
Okay, so the entire space has dimension 2D, fine. Now, can I ask you, and I have a question which is a little bit off topic, but I would be very interested in the question. Suppose I give you the gamma ij, if one can always do an associated symplectic structure. If you know anything about that, I would be very interested. Maybe we write an email. So in your case, your ij are determined. Is this correct?
Sorry?
In your case, the gamma ij are determined in terms of the given theta ij to some extent, or are they arbitrary? Or
yeah, well, first they can be constructed from. So you have this theta given, and you need to construct this gamma, right? So you know how to construct this gamma from given theta, but it is not unique, as I explained. The symplectic embedding is not unique. So you can obtain different gammas for the same theta, but how they are related, I explained on the last slide.
okay, I wrote an email. Thanks a lot. Yeah, thanks.
And there was one more question. Pedro.
Hi, Vlad. This is Fedele. I suppose
Hi, Fedele.
Harold wanted to do the work in reverse, but you will discuss with him later. No, my question is, I and J, none of them can be time-like, can be time. Can you do it nevertheless with the usual kappa Minkowski, so where one of the coordinates is time and the other is space-like, by introducing a fake, well, a momentum corresponding to time, which would be the Hamiltonian, but some sort of hyper phase space. Can you do things anyways, or so in this kappa Minkowski that you do? As far as I can see, this AI is a space-like vector, no? Or am I wrong?
No, it can be any actually. I just used here this in Latin index I, but it can be any. It also can be time-like. I think it is discussed in that paper with Patrizia and Max. I think so. And actually, for example, even here for SU2, you can work in 2+1 dimension, and then instead of SU2, you will have SU11. Right, or just like recently, Patrizia and Max did, they added some additional commutative coordinate. So you can add here some commutative coordinate, and even so, in principle, everything goes through. And this commutative coordinate, you can you can say that it is time.
But they have some interpretation, because some of the elements in your Poisson bracket, you have a Poisson bracket between time and something else. So in general, we don't do Poisson involving time. But anyways, even in this case.
Yeah. Thank you. This is a very good question, because you will have the Poisson bracket between time and something else. But that something else is absolutely auxiliary. That will not appear after that. We exclude these auxiliary variables by imposing this constraint. So they will not appear after.
Okay, thank you. I think that.
So let us thank the speaker once again. And our final speaker for tonight is Iva Lovrekovic, and her talk is about three-dimensional conformal higher spins and holography. And you have 15 plus 5 minutes. Okay, you can begin. The green light should be on.
Okay, thank you for the opportunity to give a talk here. I'm Eva from Vienna, and I will talk about three-dimensional conformal high spin theories and holography. It's a work done with Maxim Grigoriev, Daniel Grumiller, Denis Corfu, and part of it is already online and part of it is in preparation. So first, I will introduce and motivate why would we even study conformal higher spin theories. Then I will talk about conformal gravity as a spin 2 case. After that, I will continue with new conformal higher spin theories that we considered, their holography, and the boundary conditions that we imposed. And at the end, I will summarize. So we all know that the Chern-Simons theory in 3 dimensions is very special. So we know that its action for SO22, which is isomorphic to SL2 plus SL2, is a gauge theory for Einstein-Hilbert action, basically. And this construction was the first step towards getting higher spin extension by replacing the SL2 algebra with SLN algebra. Now, conformal gravity in 3 dimensions, we can interpret as a Chern-Simons theory and as a gauge theory of conformal algebra SO32. So, conformal high spins have already been studied by Fradkin and Linetsky and Pope and Townsend. So this is correct. Click again. Why can't I click? I need to go back. Just this one worked up till now. I mean, I can talk without the slide. It's better with a slide.
You need the pointer or?
Yeah, the pointer doesn't.
Not the pointer in your presentation seems that
Yeah, it has many slides because
that's why it just delays to load the next slide.
I didn't stop it, but it could be fine.
We'll give it a go. Thank you.
Okay.
You can try this one.
It's not a pointer. It's not a pointer.
Okay.
So the conformal high spins in 3 dimensions first appeared in studies by Pope and Townsend and Fradkin and Linetsky, and these were theories with infinite number of higher spin fields, and they came from the conformal higher spin algebra in 3D, which was actually 8 in 4D, and they gave the consistent theory for conformal higher spins. So conformal high spin fields are also called Fradkin-Zetlin fields, and they are symmetric traceless tensors which has linearized gauge symmetries of this form. And in the literature so far, they were studied using the high spin algebras that were known from the symmetry studies of high derivative preconformal theories and partially massless field in ADS4. But this will not be our case. So the difference in our case is that we are going to have finitely many fields. So we are going to have infinite number of theories, but each of the theories is going to have finitely many fields. Higher spin theory is important from several aspects in string theory, and one of them is to better understand ADS-CFT correspondence. And once we want to consider ADS-CFT correspondence, then it's a really good idea to start from lower dimensions because it's easier to do calculations. And in 2+1 dimensions, we have particularly rich asymptotic symmetry. The pioneering work was done by Campelloni, Fredenhagen, Fenniken, and Thijssen, and Hanada and Suyong-Ray, and they generalized the Brown-Hanada study of three-dimensional gravities. So they showed that the massless higher spins are dual to two copies of W algebra with a central charge, which was the same to the one that was obtained by Brown and Hanada for three-dimensional gravity. The work so far have been a generalization of the spin 2 cases of three-dimensional transformers gravity. So this is going to be our idea as well, because it's easier first to consider two-dimensional case and then generalize it to higher spin. So we are going to consider, from the holographic point of view, boundary conditions which are different from Brown-Hanada boundary conditions. Because these are not the only ones that incorporate stationary black hole solutions in GR. There are also these boundary conditions will lead to a solution known as black flower configuration that have infinite number of U1 charges. And they basically modified the boundary conditions for black hole solutions with higher spin fields. The most generalized boundary conditions for Chern-Simons gravity with S22 gauge group are those that have 6 charges of 6 chemical potentials and define a sympathetic symmetry algebra, which consists of 2 copies of affine SL2K algebra. So these are going to be the other type of boundary conditions that we are going to consider. So basically, from the constructions as itself, as we are going to see, one can expect that the gauge algebra, well, that final asymptotic symmetry algebra is a loop algebra underlying gauge algebra. Okay, so let's start by remembering conformal gravity. So I'm sure that majority is familiar with the construction by Horn-Witten, where Chern-Simons action is written in this form using Lie algebra valued 1 form omega, where Lie algebra, underlying Lie algebra is SO32, and the generators in which we write this field are Lorentz, rotation, translation, special complement transformation, and dilatation. We write gauge parameter in analogous way. So the equation of motions that curvature to 0, and we get from them that cotton tensor is equal to 0. So now we are going to consider new algebras and get this infinite number of Ratkins-Setley fields with high derivative gauge transformation. And for that, we are going to need higher spin extension of SO32 algebra, algebras that have SO32 algebra as in subalgebra. To construct this finite spectrum of Ratkins-Setley fields, we need to take non-trivial finite dimensional reducible representation V of SO32, which is a reducible tensor or a spin tensor, and then we need to evaluate universal enveloping algebra, it's D2 in the V. That means we have to multiply generators SO32 in this representation and find this algebra HS3. When we write it in the mathematical form, It's the endomorphism of V and the V product of V star. Now we want to decompose it into irreducible SO32 modules that determines our spectrum. And all these relations that we are going to use are well known from the literature. Now let's illustrate this on an explicit example. We take HS of a box and we take the tensor product, and then we split it into as two bases, and we get antisymmetric part, symmetric part, and the scalar. So in general, the algebra is a matrix algebra of 3+2 generators, TAB. And the commutation relations are those of GL32. And in SO32 base decomposed, then we have antisymmetric generator, symmetric, and a scalar one, which commutes with everything. So the commutation relations for the generators are also known from the literature, and we now have to use them in the composition of our equations and gauges in fields. So we can write for first example, like in basic example, in this form, where we have antisymmetric, symmetric part, and antisymmetric part will give us that one Fredkin-Zetlin field. Symmetric term will give us that three Fredkin-Zetlin field. So these are the gauge transformation. So in general, for high spin algebra with embedding of SO32, we will need to decompose high spin into SO32 modules, and these fields are going to be determined in the free field limit. So the gauge field is in general going to be written as omega AB, where we have S-1 indices here, and the S-2 indices, and gauge parameter is going to be written in this way. So we can see that this map is going to be valid. And all the remaining components of omega are going to be gauged away with gauge parameter, fixing gauge parameters, except this one component of omega, which is symmetric and traceless, and we have called it phi. Okay, so this is what our series have been consist of. It's going to be conformal graviton, and in the simplest example is going to be this spin 3 field, which I have shown. And now when we consider holography, we are going to focus first on the general holography of Chern-Simons action, and then we are going to be able to use the boundary conditions on this different theories. So Chern-Simons action splits into ADN decomposition in 2+1 decomposition, where we have two-dimensional spatial manifold sigma. We have dynamical field with satisfied Poisson bracket, which is just remember this one, and the T component we are going to treat as a Lagrange multiplier. So one also has to add boundary term, which depends on boundary condition and needs to be included to ensure that the action is gauge invariant. Now we vary the action with respect to omega t, and we obtained a constraint which satisfies Poisson bracket algebra. So that means that these constraints are going to be generators of gauge transformations that act on a phase space. So these generators, we can write these new generators with the added boundary term j, which makes it differentiable. So when we vary the generator, we notice that it's not well defined unless we add this charge. And our gauge parameters eta are going to be dependent on the field linearly. So by variation of this generator, we are going to get this charge, so to make it well defined. And by taking the algebra of these charges, after additional fixing of the boundary conditions, standardly for Chern-Simons action, we are going to get the asymptotic. We are going to get the algebra of the charges, the basic asymptotic symmetry algebra. So these two are in most cases equivalent. Now charge J evaluated on the is evaluated on the parameter which is equal to the Lie bracket of this deformation vector psi and zeta. And the additional term here is the central charge. Now we can go to our specific example of conformal graviton and spin 3 case. So we need to take into account that our field can be written using this transformation where B is an element valued in the algebra, and we choose it to be dependent on rho. This is a choice that we can always make. We can partially fix the radial gauge. When omega conformal gravity, we expand again in analogous way as before in generators of conformal algebra, where we have fields that multiply them and call them diffeomorphism charges, Lorentz transformation charges, special conformal transformation charges, and wild charge. And these are analogously charges which belongs to this spin 3 field. And they are allowed to vary. We define the H parameter in the analogous way, and any transformation of this form, which psi conformal gravity for spin plus spin 3 conserves boundary conditions. So we can determine the infinitesimal charges of the state-dependent functions under transformation that preserve these boundary conditions. And we need this to evaluate the charge. So using the expression from before, we can obtain that our charge is given in terms of these functions and fields that we call charges. And since we have integral defined, we can extend this in Fourier modes. And we are going to obtain the asymptotic symmetry algebra, which is a loop algebra of the underlying gauge algebra, which you can remember from seeing before. And there is this central extension, which is defined by this invariant bilinear form of the representation. So that's what we have seen with the most general boundary conditions that we could have imposed. So you saw that the composition of our field omega was taking into account all the generators that we have. So now we want to restrict it a little bit more. So we go from this, what we call PKLD basis to WL basis. And in this, we know how to impose near horizon boundary conditions, which we want to consider next. So technically, the near horizon boundary conditions just require that the matrices that represent our generators are diagonal. So we could have done it in PKLD basis, but there are some particular simplifications that happen for WL basis, so it's more convenient to use. And we didn't consider any particular embedding. So on our example, conformal gravity spin 3, this is essentially SL5 algebra. And after finding the map, we can write it. We can write our boundary conditions in this form, where we denote dynamical fields of charges with J. These are diagonal generators in SL5 of SL5 in the WL representation. And here we also take the Lagrange multipliers. Our chemical potentials are going to be constant, fixed at the boundary. We expand the gauge parameters analogously. And after doing all this procedure as before, we obtain charge, which then, after using Braided decomposition, gives asymptotic symmetry algebra that corresponds to U1 currents. All right, so what I also wanted to say is now, when we have this near horizon inspired boundary conditions, we can take a look what do we get in the metric formulation. And for this, we have to specify our group element B. And we take it to be of this form, with Ty plus and Syy are generators. So this one is from the set of antisymmetric ones, this one's from the set of symmetric generators. And
you have 2 more minutes.
Okay. And this is second to last slide. And when we take this into consideration, introduce into our gauge field and select the components of the Vierbein, we can write the metric. And after a lot of transformations of coordinates, we come to this form, which is conformal invariant to Lobachevsky metric. So this is just one example. But other than Lobachevsky metric, we can also get different solutions from different examples of theories. So for example, from the SL4, where we get bit Z and the generalizations that appear in conformal gravity. All right, so what I have shown is the infinite class of models for conformal higher spin gravities, which extend the one of Pope and Townsend. There are infinitely many examples of these theories, and the theories have a finite number of higher spin fields. The holography of the theories admits near horizon inspired boundary conditions, and they can be generalized to all the models of the new series. And we have also seen that we can impose most general boundary conditions as expected, which will give loop algebra of underlying gauge algebra. And it will be true for all examples of the new series. All right. Thank you.
Thank you for an interesting talk. Are there any questions or comments?
So when you say near horizon inspired boundary conditions, could you clarify, or maybe I missed that?
Yeah, well, I can say near horizon boundary conditions. The question was whether one can get black hole solutions with these boundary conditions. From the literature, it was known that when one has a regular gravity theory, then you can get black hole solutions, but here we didn't know if we are going to get them. I mean, we could have anticipated, so we just called them New Horizon inspired.
But they do look like what the field should be doing in a black hole background, except you don't know if you have them. Or yes, okay. Thank you for the nice talk. Just an historical remark. This conformal gravity is originally in the papers by Desert, Jakiv, and Templeton. It went under the name of topological massive gravity. They just write it in a different, slightly different form using the Christoffel symbols. But I think it's fair to recognize that.
Sure. You mean with a Lagrange multiplier and the torsion constraint?
The Horner-Witten paper starts from their work.
Yeah.
Okay. They just.
Oh, you mean before Horner-Witten?
Yeah. Before. Horner-Witten.
Okay.
Thank you. Are there any questions online? Okay, if not, then let us thank the speaker again. And before concluding, probably George has some instructions. So 8 o'clock down the road. Okay, so this is the end of